Greetings, everyone. We are going to a new chapter, and for the next couple of sessions, we're going to do a little bit more of, if you want, applications of first order. So we stick a bit to first order, but we do a little bit different things now. And some of these things I'm going to go over very quickly because I don't think they really belong into differential equations. But the course is supposed to be introduction to differential equations, which are, as we will see shortly, prevalent. They're ubiquitous in all of sciences, and so it's good for you to know what they are and how that some of them can be solved, but also that many times we don't really know how to solve them, and so we need methods to just calculate them because they are describing real life phenomena. So how do we calculate things if we cannot integrate or if we cannot solve the differential equation? So even first order, so remember our first order looks something like this, and we have seen a couple of techniques, but I hope it is clear from the list of techniques that we have seen that there must be many more differential equations, first order, that don't fit into that list of techniques. They are not exact, can be not transformed into an exact, or separated variables, they are not linear. So what do we do in these cases? Well, in that case, we are kind of forced to what is called numerical methods. So this Euler's method is a particular numerical method. There are several more. They are all kind of similar, and so I decided to only deal with 3.1. But you could look also at 3.2, so numerical methods. Let me write that down here. See also, so this is kind of a reading task I give you. See also 3.2 and 3.3. Okay. And what is this try to do is, okay, so we are given a concrete, and I'll write down already, I'll do a lot of my examples based on this differential equation here, linear differential equation, and with an initial condition y is 0 is 1. Now I should warn you, this one actually can be solved, and we actually can find a solution. So let's say for yourself, I'm not going to do this, so I'm going to leave it up to you. It's also in the textbook, they don't do it so. Find solution of, and I'll give the hint of this linear. This is actually a linear differential equation, and we know that we can do this. Well, up to integration, but even in this case, integration. Well, integration could be rather, no, integration is not going to be that bad here. Okay. So, find the solution. But we're going to pretend that we don't know this. Like, okay, we skipped chapter 2 and we went straight to chapter 3 and said, okay, I want to find the solution. In fact, perhaps something more, this is a real life problem, and at time 0, this is, let's say, I don't know what it would, imagine something, and I want to now know what happens at, say, time y1, or what is y1. So I could ask, what is y1? Okay, fair question, right? We know this is a function, and so how would we do? We can visually look at it, right? So let me remind you that we have I briefly introduced you to these direction fields. So let's go back to show you here, and I already set it up for this equation. It's a little bit cumbersome to input this here in this thing, so it took me a couple of tries to get it correctly. Because also, you see, I changed the dimensions here, the display dimensions. Look at, so we go from 0 to 2 in both the t direction, which is the horizontal direction, and the y direction. And then, okay, so remember we were dealing with, I don't know what I can write on this one. Last time it gave me a pen, but I don't think it does. Right, give me a pen now. The condition was that at 0, if t was 0, then y was 1. So this corresponds to this point, right? So I'm going to click on this point, and you see now that this gives me the solution curve. Because what does it do? I told you how this works, right? You start at this point, I still have to pen. Sometimes I get a pen and sometimes I don't. I don't really get it. Oh, yes, now I have a pen. Okay. So can I use this here? No. Sorry about this. How to minimize pencil settings. No, that's not what I want. Sorry. I think I cannot show you. So I'll go back to and I'll write it down for you. But what it does is it follows the arrows, basically. Okay? And so it finds the curve that fits these arrows. You can see it a little bit that these arrows are kind of leaning along this curve. So you have to imagine this a little bit. If you increase the number of arrows, so let's see that we can increase this here. Let me make this into, say, 60 arrows and then do it again. So you see now the arrows even small. When you do too many, then it kind of becomes invisible, or you cannot see anymore what happens. But again, you see the curve kind of follows the arrows. Okay, so the solution that we are looking for looks something like that. And I was asking what happens at y is 1. So we see y is 1 is somewhere down here. So it's supposed to be something like 0. I don't know. Guess something, right? 0.25 or something, 0.2 perhaps. Okay, so how do we do this? Well, so let me make a little picture of what we have, right? So we here is the same picture that we had, and we started here at 0, 1. So we're gonna basically, let me make a table. It's much easier to work with a table here. So we have an x, we have the y, and then we're gonna calculate what? Y prime. Okay, how do we do that? So let's start with, well, the point here is x is 0, y is 1. Notice that we don't know, how should I say this? Now x and y are, we can choose in that picture that you saw, we can choose any point, and any point will give me a solution curve. It's, at least in the situations that we are in, we will always get a solution curve. There are sometimes points where things don't exist, or where weird things happen, where, for instance, the function is undefined. But assuming that we are not in that case, we can take any point. In other words, any two coordinates here that I choose, x and y coordinate, I can do something. How do I calculate y prime? Well, it's actually very simple, because you know what y prime is. This formula tells you what y prime is. So you just plug it in. So in our case, so here is our equation, right? So perhaps we should write our equation in that form. Y prime is minus 2y plus x cubed e minus x squared. And so we just plug it in there. So if I plug in x is 0, that means that the second term completely disappears, right? And then I plug in 1 in the first, so I get negative 2. Okay, what does that mean? Negative 2, we know negative means pointing downwards, so this arrow was probably pointing down, something like that. Okay, with slope 2. If you want, you kind of does that, right? So it goes 2 down as it goes 1 across the slope, right? Okay. And that, now I said in these direction fields, we don't make the arrow, the size of the arrow doesn't matter that much. It's the direction that matters. And Euler's method says, well, okay, but why don't we keep the size of these arrows, fix that size of these arrows? And so the size of the arrow, we're going to call this h. And so we're going to keep a fixed size of arrows. So let's go back here. It actually, arrow length C, it has 15 here. So I don't exactly know what 15, in what measurements that is. It sounds like me, it must be 0.15, right? So if I make these arrows a little bit smaller, so let's try to make it, let's say, I think, as I said, I'm not sure what that means, 15 here. It's clear not 15 units, because that would be an enormously long vector, right? So, let me go back to 40 here, because otherwise I might not see really what happens. You see they are getting a little bit smaller here. But the number of errors, of course, the problem is now, okay, so again, let me put here, this is the curve that we're looking for. Oh, sorry, I aimed a little bit wrong, but okay, you can imagine it, right? And so you see the curve follows the arrows. So what we ideally would have is that when one arrow ends, we get a new arrow, okay? So perhaps if I increase the number of arrows, I can get to that situation. I have to play a bit because, as I said, I don't exactly know what these measurements mean. I think they, just for visual purposes, the arrows are never going to touch each other. So, but what we really would think of is, well, let's make the arrows all the same size, and then so we have an endpoint here, and then we have a new arrow, and then from this endpoint we're going to have a new arrow, perhaps it's going to start pointing upwards, and then a new arrow pointing upwards, and a new arrow pointing upwards. This is not the particular example that we saw, it doesn't happen like that, but it could be something like that. And then, at each time we calculate this new point, that should be a good approximation. And that's the idea of Euler's method. Okay? So, how does that work? Well, it's very simple actually. So, let's write down. So we start, this is, so what we're going to calculate is various points on this curve. Well, it's not going to be on the curve, but we're going to take various points and we're going to say these points kind of form a curve that is equal to the in solution curve. It's not exact, it's not going to be exact, and we'll see that there are going to be errors. So the first point that we make is the point x0, y0. So mathematicians very often like to start at 0. So stage 0, time 0, right? So that's the first point. So the first point will be point x1, y1. Okay, so let's now think of this as a very general, this is the general case. So what's the formula? Okay, let's write down the formula. So what is y1? Okay, so what does it do? What is y1? We go from the point, so let me make the picture a little bit bigger that we see what is going on. So here is our x0, y0, okay, and we have a vector of length h that then ends in the x1, y1. Okay, so for those that have done linear algebra, they might know perhaps how to write that down, but it's not so difficult for us either. Let's think about it. What is the slope? It is rise over run, right? So this means that to y0, we're gonna, so what is the y1 value? The x1 value, what is that? So, okay, I said the size of the arrow is going to be the same. I should have been, sorry, this is not correct what I said. The size of the arrow, that's one thing we could do. But the numerical method, Euler's method, so this is one possibility. Is to keep the size of the arrow fixed. However, in Euler's method, so let me now erase this. And so in Euler's method, sorry, I shouldn't have erased this part here. In Euler's method, we're gonna keep something the same, namely the horizontal direction, the horizontal length, the horizontal dimension of the vector. Are we going to keep the same? So in this picture, it's not this h doesn't go here. Where does h go? Horizontal direction is, we're talking about this is h. This direction is always going to be h. Okay. So what does that mean? Well, what does this mean for x1? Let's first write down what it means for x1. For x1, it means that you just add, okay, let me perhaps get rid of this line here, because we are not necessarily at the origin anymore, right? So this line is not there, right? The origin is somewhere in general here, the x or y axis. So I start from this point x0, y0. I have this arrow that points down, but I'm restricting the size not of the arrow itself, but of the vertical dimension of the arrow, the vertical direction of the, the horizontal direction of the arrow. So what does that mean then, x1? Well, x1 is you just add h So this was x0, right? So x0 would project down here, and this would be x1, and the difference is just h. So this is this formula for x1. So what is now the formula for y0, for y1? Sorry. Well, for y1, we have a slope, and the slope in this case is given by this formula pxy, and the slope. So this slope. So this vector. What is the slope? Well, the slope is px0 y0, correct? Right? It is the slope is given by the slope of y prime at the point in the first point in point x0 y0 is just plug in x0 y0. That's the initial condition if you want. So that is the slope. Okay, so I'm gonna not check this. You can easily check this for yourself, that the actual value therefore is that. So, and this is our formula. So y0 plus h times the slope. So we go h units in the direction of the slope, and that's why we get, so that is this thing that we get here, this distance, okay, and that is where we end up in here. And then we repeat. We have here now we have here now a new vector again with, so let me do it in different color. We have again a new vector here. This distance again h, so x2. What would be x2? Let's write down. x2 will be x1 plus h, right? Again, we go h further. And what would be y2 be? Well, the same thing. We have to y1, to this y1 now, we have to add something given by, sorry. H times the slope at this point. Now, what is the slope at this point? Slope is now, well, we are at the point x1, y1, so you put in x1, y1 in P. So x1, y1. Okay? So let's write down what this means. So what are we trying to do? We're going to do this in many steps. So for instance, remember, our original problem, we said we want to calculate this. Now you can do this in one step, but it's clear that this is going to be extremely wrong, right? If you just think of it, if this would be, if the solutions would be a circle, so sorry, let me go back. I don't know, I can do this. Okay, perhaps. If I have a circle like that, okay, and I say I got to, with step one, the circle would bring me there. You see that that's not the same as where if this is x0 and this is x1, and suppose the curve is a circle. Now at this point, the slope of the curve, which is what we call, is exactly this direction that I drew. It's, by the way, if you want to know how do you find that direction, it's perpendicular to the radius here. So this is the right angle. So you see that after just one step, I'm actually kind of far away from actually my circle, because my circle curved and my vector didn't. So if I take two big steps, I'm gonna go completely away from the actual curve. So I have to keep my steps small. That's the one idea also in calculus all the time, right? This is the same h that we have been using in when we were differentiating, when we were trying to find the slope of the tangent line. What we did then, instead, we would look at the slope of the secant line, and we made h was the difference between the point that we're interested in and the intersection point, and then we let h in limit go to 0. Now we're not going to take limits because we're going to actually calculate this. Okay, so h has to be small. That's one thing I wanted to say. So if I want to do this, for instance, if I want to get, say, I want to calculate y1, right? This is my question. I should not do this in one single step, but for instance, I could do this in 4 steps, or in 10 steps. Okay, so so we can take h 0.1 or h at 0.25. I will later look at the tables and see what the results are, because the calculations are tedious and we're not really interested in that. So this is more a little bit of, if you want, there will be some homeworks, but it's more illustrating how these things work. So if we do, by how many steps do we do then? Let's think about this. If h would be 0.1, how many steps do we need? 10, right? 0.1, 0.2, 0.3, after 10 steps we will be where we want. If h is 0.25, 1/4, then we have to do 4 steps. Okay, that's quicker. But so it's clear now, the smaller that h is, the more steps you have to do, but the better you keep clean near your actual solution curve. Okay, so what does it mean therefore is, let's focus on the first case here, that this is 0.0. So we need 10 times to do this. So we want to write down a formula for how to calculate this one. So we would have xi would be xi plus 1 is xi plus h. So what I'm trying to do is, I said, okay, in my calculation at some point, after I calculations, I found I, so I is going to be here 1, 2, all the way up to 10. And when 10 is there, we are exactly where we want to be. So I am at stage I is say 7. After 7 steps, I'm here. And now I want to calculate the next step. Let's say that the vector is pointing this way. And so this will be xi1, yi plus 1. So the subscripts here indicate the steps, the points. The list is index for the points that we're calculating. And how do we calculate? So the calculation of xi is basically trivial. It's just added h to it. And by the way, if you think about it, this is actually equal to, you have each time you add h after I plus 1 steps, you have added hi plus 1 times. Okay. So, but let me not write this here. So let me take this away here. Just then you see it much more systematic how it is. After all, we have to calculate these things, so there's no need to have a general formula here. And y plus 1, that is then the previous yi. From here we start. We go down. We follow the arrow for this much length, and the slope of the arrow is given at this point. So the slope is given by the formula. So I'll write it down here. This is my formula for the slope. So it is given by, so the slope is pxi yi. Okay. And so then we calculate this, and so after 10 steps, so y10, that will be a good approximation. Well, we'll see about that, but this should be somehow the same as y1. Why you might say 10 here and here 1. Well, I'm getting confused. Where's the 10 come from? The 10 comes from this case. The reason is that I started from 0 and I went with increments of 0.1. So after 10 increments, I was at 1. Okay? So in general, of course, if you want to write down what this means, yi would be the same as y x0 plus I increments. Which is, by the way, just xi, right? That's what we called xi. Okay? Right? So, what I'm saying, therefore, is that, so let me repeat, therefore, that yi, that I calculate using this iterated calculation. I have to iterate this, right? This is recursive, if for those that have done, seen a little bit, oh dear. Discrete math or other programming. So for if I do this after I steps, what I have calculated is something that is very close to the actual value of that function at xi, where so I is the solution of this equation, of the differential equation, going through the initial condition, having the initial condition y of x0 is y0. Satisfying. So perhaps in saying going through, let me just say satisfying. The initial condition, this one. Okay? And the smaller h give less error. That is a principle, if you want, that's basically the principle of calculus, is that the smaller you take the h, the smaller your error is, and so the better approximation you'll get. Okay, so now we can do this in practice. So I think, let me scroll up here, I copied a couple of tables here. Yes, so here you see the first table. Let me see, can I point here with my finger? I want, my pencil is getting out of juice, so but I need the pencil to point here. I don't have any, yeah, I should get 2 pencils, but okay. So, okay, here is, in this first table, you see the table here on the top. That is the equation that we talked about, and here is exactly the 10 steps that I described in the first column, h equals 0.1. So they did 10 steps there, and each of the steps you see the calculation. So the calculations is exactly what I said I'm going to do here, but then doing it with the concrete equation, with this concrete equation here, right? So let's just for the heck of it verify that the first step is correct. So let's do this. So y, oh sorry, our equation. Where is? Let me copy it here because I wanna. Okay, so this is our equation, and so now we wanna. So we know that x0 we said was 0, right, and y0, so right, we were making a table, x0 is 1. So x1 is x0 plus h, which in this case is 0.1. So remember, h is 0.1 and x0 is just 0. y1, here is of course the calculation. I write down the formula. And so now remember that this is our p here, okay? So what is p? So we have to, so here's the table, right? So x, here is x, so let's say here's the steps. So okay, let me make a little table here. Step. In this first step we have x0 and y0, and then here we have p. So p of x0, y0 is, this case, so this is how the, sorry, I'm setting up my table here, and then the next one was x1 and y1, okay, and then, so this will be p x0, y0, and here will be p x1, y1, etc. Okay, so what is this now? Okay, I'm making the table again, but now with the actual values. So here, steps, 0, and this is 1. In step 1, x0, we said is 0, and y, so this is the axis, xi, and this is yi, and this is p of xi, yy. So I give now, depending on I, that's what I calculate. So x0 was 0, y0 was 1, so what is it? What happens if I plug in 1? I think we did that already, 0, 1, that was negative 2, right? Okay, so we can now calculate y1. y1 is y0, which is 1. Now look, all the information that I need to calculate is in this column, in this row, okay? So it's 1 plus h, which is 0.1, well, except for h, of course, it's always the same, times minus 2, okay? So this would be 1 minus 0.2, that is 0.8. So let's plug it in. This is 0.1, this is 0.8, okay. So let's do now y2. Well, x2, what is x2? Well, remember, x2 is always, you add another 0.1, so we kind of know what this is going to be, right? This is going to be 0.2 here, okay? And then in the third step, it will be 0.3, etc. Okay, but let's look, so the only calculation really that goes on is y2 here. So what we need for y2, I write down the formula, is y1 plus h times p x1, y1. So we need this row, but we're missing something here, this one. How do we calculate that? Well, you remember, it's you plug in these two values in there. So I'll write this here. So this calculation, that is p of 0.1, 0.8. Now this is where it gets tedious because we're going to work with fractions, right? So we get minus 2 times 0.8 plus 0.1 cube times e minus 0.1 squared. Now, I'm not going to even attempt to try to work this out. This is a numerical method. That means the only thing we really expecting to be, the thing that we are allowed to use all the time is a calculator, right? That's the whole point. So let's look at what this is. This is what this table here, the first table that I showed you, is doing. It calculates the value here. So, okay, on top it said h is 0.1. That's the table is arranged differently, but you look in the first row. Remember, we said the y value is 0.8, y1. That's fine, we'll find now. So in 0.2, the new value that we get is 0.64. Oh no, sorry, this is, okay, sorry, did I, oh, okay, no, sorry, we have to still plug this into this formula. So I have to actually calculate this, that's a bit annoying because okay, let me try, I'm going to use my calculator here and tell you what the value is. My calculator is not a very good calculator. Oh, let me do this way. Give me a sec, guys, I have to set up here. I'm going to use Wolfram Alpha on my separate iPad here to calculate this for you. So it is, yeah, but it's a bit easier if I do it minus 2. Sorry. On an iPad, to get minus 2, 0.8, close the parentheses, plus, I'm sorry, I should have done this separately, and now let me go here. It's, because I wrote it down here. Yeah, okay. Sorry guys, I'm gonna have to do this here because otherwise there's no way I can, this is gonna take forever if I have to do this on a tiny calculator like that. So it is minus 2 times 0.8 plus 0.1 cube e to the minus 0.1 square. I don't want to work out everything, I just want to put it in a calculator. So I'll go here and I use Wolfram Alpha. Wolfram Alpha, here you go. Okay, so here now I can easier put it in minus 2, 0.8 plus 0.1 cubed times, I better write here a time, e to the power minus 0.1 squared. Okay, I think it says it's minus 1.5. So let's see here. I press here to see that he understands what I'm asking. So you see here the first line input. Is this what I wanted? Right? Because I'm writing down something, he has to interpret my writing, right? And this is exactly the thing that I want to calculate. So he's answering me the correct answer, and so it is minus 1. I mean, I'm not saying he answers me correctly. He's interpreting it correctly. So rounded down, it's like minus 1.6, right? Let's write it. Let's say it's minus 1.6. Okay, going back. So we know now that this is minus 1.6. Is minus 1.6. So what is this now? We have to still plug in. Y1 was 0.8. Oh, sorry, I should write it here. Minus 1.6. So now I'm using, let me highlight it, this row to calculate this expression. All the data that I need are there. So this is equal to that plus 0.1 times what I just calculated minus 1.6. So if I do this, I get 0.8 minus, be careful, multiplying these two means the decimal is gonna, so it's minus 1/16, right? 1/10 of minus 1.6, the decimal moves 1. So I'm doing this in my head because this one, 0.64. Let's see what the table says. And that's exactly, I mean, I rounded down, so you see it's there. They wrote 8 digits. I'm happy with 2 or 4 digits here. The reason that they do so many digits is because they want to compare the various methods here. So that's how you get the second row, at least for h is equal to 0.1. But you see, it's a lot of calculations, right? And so to do these calculations, you have to put up, you can set this up in your calculator, or you can do some, you basically have to define tables. In your calculator, you can set a table, right, that calculates these things for you, or you can use Excel or something in that to do these calculations, or you can write your little program to calculate these things. I'm not going to be too concerned about that, and you see in the homeworks they want to ask you to do, I did now 2 steps, and they perhaps ask you to do the 3 steps, so all that can be done by hand. Okay, by hand meaning step by step, as I did, rather than this table here. Now that we are this far, let's discuss let's look a little bit more at what is data AR. So if we do these 10 steps, let's keep looking at the column that has the label 0.1. That was where we're working, right? So we had calculated the 3 first values, 1, 0.8, and 0.64. Remember, this table lists the y values. And what we want is exactly the 10th one, because we said the 10th one should be approximately the same as y of 1. Remember, 10 steps, after 10 steps we were at the value x equals 1. And according to this table, if you do this method, it says it should be 0.13977, so rounded down, say 0.14. Okay? This is if we do this with steps of 0.1. If you think of it as if we make our vectors in the vertical that length at 0.1. Now, the smaller that's one of the principles of calculus, the smaller we make, the better the estimate will be. I say this is a principle of calculus. This is really what continuity, that's the principle of calculus that is behind the idea of continuity, just for information. So let's now take a smaller h, half the size, 0.05. Now, be careful. How many calculations do I have to do in order to get to the value 1? The x equals 1, right? That is the very first column in this table, that is the x values, right? There I have to do 20 calculations, right? So the very last number, the 0.1547 in that column above, in the column 0.05, let me see, I charged a little bit. So in this column, remember, these are the y values when the h is given by that. But which one is this? Is this y1? No, because 0.1 would require me 2 steps. So this one, so let me write it down here. So this, right, so this one we said here is y2, right? And this one was y1. In this calculation, this is already y2. They didn't write down y1, but it is an intermediate calculation, right? So remember, the smaller you take, the more steps you're going to have to do. So this one was y10, but if you take half the steps of half the size, well, you're going to have to do twice as many steps. So this is y20, okay? And then in 0.025, that is again half of the previous one, so you're going to be 40 steps, right? I understand all these, what goes into this calculation. So they don't show you, in the case of this case, they only show you every other step, and here they only show you every 4 steps, right? This would be what? y4, right? You have to do 4 times this before you get at x equals 1, okay? Okay, so, and by the way, I said we have a solution of this, and is it written down here? I think I just did not copy that one, the solution here. They have a solution so they can check the actual solution and compare. And now let's look at just the bottom line here and compare here. Okay, let me I'll highlight this bottom line, and then I'm want to put my pencil to rest once in a while because it needs to charge. So you see that the values are not all the same, but as you move to the right, meaning as you take lesser steps, the values get closer and closer to the actual value. Remember, we know what the actual value is. So in particular, if for the steps of 0.025, in other words, after 40 steps here, so when we take a step of 0.025, we need to do 40 steps before we get to 1. That gives us the best approximation. And it's not The difference might not sound huge, but the difference between 1.4 and 1.6 is still 0.2. It's 2%. So here the error that we make, if we go from the error, or the difference, right? If you want the difference here, this is 0.14, this is 0.16, that is 0.02. That is a 2% error, right? Difference. I mean, and its effect is worse because it's actually 1.7, right? So this still has almost a 1% error, okay? But so this is what this means. The better we are, and here it shows you the arrows. You see here S, we take smaller the exact value and the approximated value, right? So remember, y approximate 1 means, in this case, for instance, this is y40 in this calculation, okay? And you see here the arrows. They get better and better. What is the difference? Oh, the list here, this is just the arrows this was the arrow on the last line. Here the arrows at all lines. I don't know. That's not so much helpful. What does this table tell me? I'm not sure what the difference between this table is and that table. Yeah, then there's a lot of truncation errors. Okay, so here's a new equation here, where here exact is written between parentheses because actually I don't think we have an exact solution for this one, although this is so simple that it would surprise me a little bit. But yeah. And look here, the only thing I want to point out is here, okay, we have this particular equation. I think it's not a problem to find it puzzles me a bit by this. Let's see here, y prime minus 2xy equals 1. This is a linear approximation, right? So if I want to solve this, I first do the homogeneous, right? So let's do this. This is y prime equals 2xy. I'm trying to solve it now. Y prime over y is 2x. So dy over y is 2x dx. So we see that the ln of y is x squared plus a constant. We need the general homogeneous. And now we need a particular. And the particular will be, we have to solve for y here. So y is e to the x squared times e to the c. But e to the c, let's rename that as our c here. Okay, so I'm just going to call this my new constant. This is how the actual solution looks like. I see now. This looks so simple. This looks like, oh, what a cute little differential equation. Let me solve it. Okay, let's see why does it go wrong here. Now, a particular solution, what do we need to do? Well, we do y is, we replace the c by u e x squared. Right? It was the u times the homogeneous, some homogeneous. Okay, so now we take the derivative. Y prime is u prime ex squared plus u 2x ex squared. Right? That's y prime. So if I plug this in, I get u prime ex squared plus 2ux ex squared e minus 2x times y, which is u ex squared, equals 1, right? This is the one. I'm plugging this in this equation. I hope you follow here. Is 1. There's a cancellation. This cancels. That's what has to happen. And then we can separate variables. So you see, Professor, why are you afraid? Look, let's just do this. Okay, bring this to the other side. I get e to the minus x squared. And so now we have to derive that if you want is du. Okay, du is e minus x squared dx. And to derive this is just u. And the antiderivative of this thing is, oh dear, what's the antiderivative of this thing? E minus x squared? No. Be careful. There's an inside function here, but the derivative of that inside function is missing. If there would be an x, no problem. There is no x. And that makes this impossible. And it's not that we are stupid or ignorant or whatever. No, one can show mathematically, it's a high level course, that there can be no formula. This function exists, but we cannot write down this function in terms of known functions like tangent, sines, or logarithms, or it's impossible. So we cannot write down this function, and that's why we need a numerical method. And that's why also this exact is between quotes here, because we don't have an exact equation. But what they mean here is they use very refined methods. The one that they use, I think, when they explain it at some point, the one that are described in 3.3, the Runge method, Runge-Kutta method, it's called here in the book. But I'm not going to cover that. So, but my point is this here now. Let's look at, let's say we want to calculate this. So we start at 3, y0 is 3. That is, of course, x is 0, and all these are 3, right? It's all the same. And what we want to find is y of 2. So question here, this calculates y2, right? X is 2 here. So let's highlight this one. Look at the values. They're kind of different, quite different. I mean, we are used to, we were talking about 2% errors. These are almost 100% errors. Well, yeah, the difference between here and this is 3 times this almost. This is huge. This errors of 300%. No way that this is correct, right? So this tells you that this method is actually not so great. It looked like it was great, but if we take our steps, these are now, okay, you might argue these steps are a little bit too big here. When we take a bit smaller step, things are getting better. I don't know whether they have improved this. What is this? Oh, so this is the new method now. And that's the one thing that I want to explain is the semilinear method. And so in the semilinear method, before I explain it, let's just do the result of this, is look how much better things have become. The values are now all rather close to the actual value. Compare this line, which is the same equation, but this is a different method, which I have not explained, but I'm going to do soon. So compare this line with this line. Sorry, I cannot put. Can I put them? I can put them on the same screen here. You see how, of course, that these two values here are the same, right? Because supposedly the exact value, but the others are way different. And so this method, but this one, the second one, they're all kind of close to the actual value. So what is this semilinear method? And that's all I'm going to say now. So let's go down again. So Euler's semilinear method. I'm not going to work too much on it, but I just want to explain it to you, and perhaps I put a homework problem where you can work it out. So the equation here that we are looking at, sorry, let me go back to the textbook here. Well, I'm going to go to my own textbook. Sorry. Give me a sec, guys, I have to pull this up. Why is my iPad is slow? Okay, so here the semilinear, okay, semilinear, where is the semilinear? Okay, the equation was y prime equals 1 plus 2xy, and y of 0 was 3, and the question was, what is y of 2? Okay, but that was what they did in the table. But I want to explain the method, so it's not so important exactly what we want to calculate, but what we do. We first of all, remember, this is the equation that I tried to solve with linear. It's a linear first-order equation, so in principle it's solvable, but we hit an integral that we cannot write down, and therefore we're stuck with that calculation. So, what did we do? Well, first of all, remember I did the calculation here. We tried to solve it, and the first thing we did was a complementary homogeneous equation, right? So we solved this, and we found that y was equal. Let me cheat and go back. We did the calculation, so I'm not skipping anything. Just don't want to do it over again. We found that this was y is cx squared. Okay, y is cex squared, and then we said we find the method from variation of parameters. This is what we're going to do, right? So this is step 2, to find a particular solution, but this is in the beginning, when we started doing the first time, it was the very first time that we did this, so we didn't give a name to it, but now we know that this is the method of variation of a parameter. So we use this, we think of this as a parameter depending on x. Okay, and we try to find this u. That's the idea. And we did that, and we found the equation. We ended up with, after calculations, we found that is our equation. Okay. U prime. So the calculation I did, so that's why I did them over there, e minus x squared. I hope you go back to look at it, right? And so this is a linear differential equation. It's actually very simple, and it really is an integral, but we can do Euler's method. So we would have x0 is let's say 0.1. u0, what is that? So we have to be a little bit careful now, right? So what we know that y0 is 3. And we know that y is equal to this thing here. That is u0 times e to the 9th. Right. So what I'm doing is I'm plugging x equals x equals 0, sorry. Not, it's x is 0, not y, right? So this is 0, right? So 0 here. I'm plugging in x equals 0 in this formula, and I know this must be 3, that's the initial condition. So 3 equals u0 times e0, so I see that this is 1. I see that u0 is actually, u0, which we call u superscript 0, is actually also 1. Is also 3, sorry, is also 3, sorry. Is also 3, okay. So now we have to calculate x1, x0 is 0, we started at 0, x1 is 0.1, we're going to do step 0.1. I'm doing only one step. What was y1? No, u1. So u1, well, let's down the formula for u1 was, just copy this formula, right? But just replace y by u's. So u, or here is the one for x for 1 itself, so it is u0 plus h times, but now this is our q x of y, but it only depends on x, so it's actually a qx here. So this is now the new function, right? So remember, you apply the method, you have to write your differential equation, your linear equation as y prime equals some expression in x and y. Okay, and it's this expression that you keep constantly using in the formulas. So in this case, the expression has become minus ex squared. Okay, so this is qx here. So let's fill in the numbers. u1 is u0, which was 3, plus h, which is 0.1, q, and now we have to plug in x0. Oh, sorry, 0 has dropped here, which was just 0. So let me not write q. Let me write down what it is. Now I have e minus x squared, and I have to put 0 in here, right? So this whole thing, of course, is 1, so I get 3.01, that is 3.1. Now, be careful. What is this? This is supposedly almost the same as u of 0.1. So I repeat, right? What this thing does is it calculates the approximate value of your solution after the 8th step, in this case after the first step. So this is approximately equal to that. So what is y0 then going to be? Approximately, it's going to be u 0.1 times this e minus x squared in 0.1. Remember, this is, so let me box it out here that it comes a bit more. This is the where you were coming from, but we don't want u, we want y. Okay, and what is that? Y is u times that. So we are calculating everything in 0.1, so we have to calculate u in 0.1, which we did here, or at least the approximate value here, that is 3.1. So we get 3.1, and then we have to calculate this here, that is times e to the minus 0.01. Okay, so let's quickly do this in Wolfram alpha. What is it? 3.1 times e to the, okay. I hope I can remember this. I'm very bad with numbers. So you can imagine how this is horror for me, to be a mathematician and not be good in numbers. That's a bit exaggerated, but okay. So now I remember, was it plus or minus? I think it was plus, right? Plus, oh no, times, it was times. Times e to the minus 0.01, okay? And it's 3.06. So we'll go back, so this is apparently 3.06. Let's see whether this here, this is Euler's method. This is, sorry, my Euler's method. No, this is another one. Here, this is the one. Okay. So, oh, they don't give it to me. Oh, I have to calculate 0.2 here. Let's assume that I did it correct. Oh, well, in fact, one thing I have to look in this table, not in that h is 0.1. So I should do it one more step and do the calculation. So what I calculated was actually the 0.1 here. I don't know why they, for some reason, gave this table. Of course, if I want to do this, okay, no, let's not. I want to stop here because all this is just tedious number crunching. I want to give you the principle. So the semi-linear method, you try to solve the equation as far as you solve the homogeneous equation. Hopefully you can do that because even that could be problematic. And once you have that, you do the variation of parameters, which in some sense is just you use here. You take a homogeneous solution, non-zero of course. So in this case ex squared, and multiply it with the parameter u. You write down what that means. It gives you an equation, a differential equation in u, and onto that one you apply Euler's method, the straightforward method where we calculate things using these formulas here. Okay. So if u2, what would u2 be? U2 would be u1 plus h times q of x1, right? There's only one x1 here, so we could calculate this. But remember, y2 is u2 times e x2 minus x2 squared. We have this extra part here, right? Don't forget that this is the one you want, not u2, but y2. That's the step that you need to add to it. And so you can now make your tables and verify the tables. So I'm going to give you some homeworks where you do a couple of steps and to calculate these numbers and perhaps even compare. And just to see, so we after one step, no, okay, we cannot really see, I get 3.06. But even after one step to see the difference between Euler's method, the comparison again on how good they are. No, I go one here. So that's okay. I'm sorry. This particular one doesn't give 0.1. It gives the values at 0.2. But let's compare them. Here it was 3.2. In this row it was 3.26, and here it would be 3.32. You see, it's already different. Okay, and it is closer to the actual value. This is the actual value here, whereas 3.26 is a bit further away. You see that we are doing much better with the semi-linear. Now, it's not always the case that the semi-linear gives you better. It is a bit hard to predict, and that makes it that it's a field on its own. Numerical methods, numerical, and in fact, I think there's a course in the math department that treats these things, and there you're going to see much more how you figure out which is the best method and what are the errors that you can expect here. I just want to very quickly say the error is about proportional to the size of h. But proportional, okay, if it's proportional, if it's about 10 times the size of h, your error, okay, if your h is 0.1 and it's 10 times that, then it's an error of 1, which is perhaps not very good. Okay, so then you would say instead of 0.1, I want to take 0.001, and then my error won't be much smaller. But proportional could be, the proportional constant can be very bad, and this is what exactly happens in this particular partial linear linear first order differential equation that we were looking at the end here, the one that we're looking at the table at, here the proportional, it is proportional to h, the error, but the proportional constant is very big. Like if suppose it could be 1,000,000, it's not that bad, but it could be 1,000,000 and then therefore the error could be horrendous. Now, of course, you can compensate by taking extremely small h's, but that again causes problems because you're going to get rounding errors. The smaller your h's, the more, look at, we have 8 digits here, but if you're going to take h to be equal to 1,000 or 1,000,000, say, then 8 digit is not going to do it. You're going to have to use 20 digits or 40 digits. So you need high precision, you need much more better calculators to use these smaller values. So it's a bit of a payoff. If you take smaller h's, you're going to get better round errors coming from the method, but your rounding errors are going to be bad. And this is the problem sometimes of numerical methods, is that where you try to improve one, you make the other one worse. So keep that's the one last thing I want to bring to you is there are 2 types of errors that can happen. The errors that come from the method, where we know what they are, it comes from the choice of steps. If we take the smaller steps, the h, the smaller steps we take, the less our error will be. But in calculations, we have rounding errors, and those can mess up the result also. Okay, that is all what I want to say about numerical methods. There is normally more that when you would talk about it, but I don't want to do this because I really want to go to the next thing we're going to do is applications of first order linear equations, and then we go to second order. Okay.